Hello everyone, welcome to the class ECE317, the digital signal processing 1. Actually, we are discussing the difference equation, how to solve difference equation with given initial condition, right? Today we will keep working on the same topic. ECE317. This should be Monday's class, right? Monday's class for the 6th week. So difference equation with given initial condition, initial values, initial condition values. Things like that. Right. Suppose this is a system S. We have input X, we have output Y, and X and Y they have differential equation summation sum a k y of n minus k run from 0 to certain l equal to summation bk times x of n minus k run from 0 to some n. Right? Then initial condition, some initial condition. We have initial values y of 0 equal to something, y of 1, negative 1 equal to something, y of, okay, how many initial value? Depending on this n, this m, depending on this m, depending on the order of this side. So here's the order m, then we need the m initial values equal to something, right? We use this initial value. Here I choose the time 0, negative 1 until negative of m minus 1 as the time to set up the initial value. So we can also use y of I say some k for any n different m different case. So the initial value you can choose any, like for example you can choose y of negative 1 to y of negative m as your initial value, or you can also replace times 10 times, and then y of negative 10, y of negative 20 until y of negative m minus 1 tenths at the time to set up your initial value. Yeah, you will have same result, same method, right? But this set of values are most common used initial values. Usually we use this time to set up the initial value. Then we will have the output or y r of n equal to y p of n plus y h of n. Here yp of n is a particular solution. You can have the particular solution from Fourier transform, from the equation by Fourier transform, the inverse Fourier transform. You can have particular solution. Now, of course, if x is given, right, you need to know what is x. And the homogeneous solution, you just let x equal to 0. So all these parts cancel, right? This part should be 0. So you just solve the equation contain y, some y's equal to 0. You solve that, and we call that equation as a homogeneous equation. And then the solution of the homogeneous equation is homogeneous solution. Then we do summation, particular solution plus homogeneous solution. We have all possible solutions. And because here YH is you have infinite, all possible homogeneous solution, right? So to summation you have all possible result. And by initial value determine the coefficients in YH of n, and then determine y of n. Y of n will be one of these YR of n. Now here you have infinite choice, and this is one of it. This is obtained from YR by, you need to satisfy the initial value, so you can determine the unknown coefficients in YH, so you can determine Y. Right. Okay, so this is the whole process. And we also discuss some initial condition on the impulse response. H of n. S is causal. That means YH equal to 0 for n smaller than 0. So you can use these as initial condition. Actually, we have infinite values. We only need m, so you can pick any m from here, then try to solve it. Right? And another way is S is a anti-causal. Oh, here it can equal to 0. Can I? No, just less than 0. Yeah. For anti-causal, then we have H of n equal to 0 for n larger than and equal to 0. So this is anti-causal. As a causal, do you remember what is causal? Causal means the value of the output will only depending on current and the past input. Right? And anti-causal will be reversely. The output only depending on future input. Oh, it sounds like impossible, huh? But certain case we need it. Like if you already have all the data, then this time you can consider this set of date for any time. Like, yeah, all right. So it doesn't matter. You can consider some future time. Yeah. All right. And as the system S is stable, according to summation of H of n will be a finite number. If this summation go to infinite, then S is not stable. So we have this one. Okay. Now let's consider some new things, right? All these are previous material. First one about this H of n, initial condition on H of n. You see, I say system and the initial condition on H. Now how about on the others? Right, the output, you different input, you can have different output. This is just one of them. You use dirt of n, the impulse as input, and you have this output. If you change different input, then can you say something about the initial value on the system? Okay, the thing like that. Firstly, you should know different input, different output, the initial condition may different. If you want all of them have same initial condition, then the system will give you a kind of a strange system, I will say. Yeah. I use an example. Y of n minus 1/2 y of n minus 1 equal to x of n. I use this one as a system. If for any, if we always assume y of like -1 equal to 1, what will happen? Actually, not just for this one. Any system. Yeah, I can talk this more general. Example. Consider system 1. See, this is 1. Alright. System 1. If we always assume y of negative 1 is 1, then what can we say? Firstly, if x of n and x1 of n, which is 2 of x of n, are 2 input, then the output y of n and y1 of n. Now y of n is the output when input is x. y1 is the output when input is x1. Now you see, these 2 input, the second input is the double of the first. Right? It's a double. So if the system is linear, then y of 1 should be 2 times y of n. Right? y of n should be 2 of y of n. But now y1 of n, when n is negative 1, this is 1 because we always assume the initial value is 1. So we have this. And y at n equal to negative 1 is also 1. Not double. Right? Yeah, if it is linear, it should be double. But now it is not double. So we say the system is not linear. Right? It's not linear. Alright. Why we have this result? Just because you assume all the output with the same initial value. This is not it's not reasonable, right? Different input, different cases, the initial should be different. But you said okay, all of you should have to be same. Then the system is not linear. It's not linear. Right? Here I said y of negative 1 is a fixed number. You can also say like y of 2. Y of 2 is always 1. Then you can do similar thing. You will see that is also not a linear system. Not a linear system. Of course, if you said this is 0, things will be good. But if we always use the initial y of negative 1 equal to 0, then the system can still be linear. Can be linear. You will satisfy y 2y of n if how to say, the s of 2x of n or equal to 2 of s xn, x of n. Okay. This is x1, and the output of x1 is y1, and this is xn, and output is y of n. Right? 2 of y of n equal to y1. And we have another one as if I have 2 signals x. Okay, I still use x and x1. X, different. Okay, x1 and x2 are any x1 and x2. Different with that x1. Any x1, any x1, any x2. Do summation in the input side, then you find the output. this output will equal to summation of two output. This is one output. This is second output. So we still have this. You can show step by step. We still have this. So the system can still be linear. Can be linear. Here is a 0. You set it 0. You can make it linear. If it's not linear, if it's not zero, non-zero value, then it won't be linear. Okay, this is one thing. And we can see we have anything else. And the time variable. Yeah, we can also consider the time variable. Okay, we go back. If we always use the initial condition y of -1 equal to 1, then the system will not time invert. Then the system will not be a time invariant system. Why? Because you shift. Like you have x of n, you have s, then you have y of n. Y of n, you suppose at n equal to -1, here should be 1, right? This is y, this is y. Now you shift. If you shift x, right? Shift x, you have x of n minus nd shifted by nd. Then you use this as input to the same system. Here will be output. So this output, I don't know whether it is equal to y of n minus nd from here to here. Yeah, shifted by nd. Y shifted by nd. You have this one. Okay, this input, this output, shifted output, and the output from shifted input here are the same. We want to know whether these two same. Alright, both, this is y shifted. I put sh, ysh. Ysh of n, the shifted, this one shifted input, get this ysh. This ysh, here should be 1. And yn minus nd is also 1. Okay. But it is shifted, right? So suppose this one should be 1 is here. This should be when this is nd minus 1, right? Shifted by nd, right? This -1 shifted by nd should be here. 1 should be here. And this value, another one here, -1 minus nd will go to here, right? You shift it. And what is this value? Only if this value is same as this one, you can keep the shift. But usually it won't be. Usually it won't be. If these two are same, you can check one more step, whether this is 1. Only if all of these are 1, you can think, okay, it's shifted, it should be same. Still not, because you also need to consider the value like from here and here. Are they same? When you shift these to here, can you make they are same? Usually you can. You can. So I will say, if you just use this unique initial value for all the system, all the output, then the system will not be time invariant. So LTI system can be described by difference equation. But by difference equation, sometimes you can have a system it is not linear, not in time invariant. Why we have that? Just because we always use some fixed value for all the output as the initial value. Yeah, we really have unique initial value for all of them. So it is not time invariant. Not time invariant. Alright. Okay. I think as a basic feature we already have for the how to solve difference equations, right? Here I want to discuss some special cases. Actually, last time we have considered special case, some special cases. Last time we say 1 over 1 minus a e to negative j omega by dt ft inverse. What is the result here? Where a is a value larger than 1. Then what will be the result here? In this case, we cannot use the Fourier transform directly. You check the table. We do not have this. So you need to make some change. The result will be, I forget last time, but I think it's after some change should be like this. Still a to the n u of negative of n plus 1. Plus 1 here maybe. Plus 1 or minus 1. Yeah, you check the notes. Here should be positive or negative. Yeah. Here's n or n plus 1. I forget. And here will be positive or negative. Do we have the note? Yeah, I have the note. I have the notes of last time. Alright, it's here. Let me make it a bit so we can see more. The example we have 1 plus 2. You see, we have this term 1 plus 2 e to negative j omega, right? We have this one. Okay, we go to here. I copy this one. It's 4 over 3 over 1 plus 2 e to negative j omega, and these go back to the frequency domain. From frequency domain to time domain, we have 2/3 negative 0.5 negative n plus 1, and the u of negative of n plus 1. Okay, I go back to our screen here. Alright, so we have this, right? We have this from here to here. So if I erase this 2/3, I have 2 here. Okay, so the result is like this. This 2 is a is negative 2, right? A is negative 2 now. A is negative 2. So this is a negative a. And if I put a here, then here is a positive. It's just this one. I remove a. If I put negative a here, right? This is negative a. If I put negative a here, this will be this one. This is this one. So now I remove that negative a. Should be, I move to this side. It should be negative 1 over a times a to the negative n plus 1. Oh no, this is a negative. It's 1 over a. This is 1 over a. So here is just positive plus 1. And the u of negative n plus 1. Right, so this one. This one. Or, okay, I can do more simplified. It is negative a to the n, right? This a and here is plus 1. It can be cancelled. Then times u of negative of n plus 1. Yeah, it is. So this one can go to here. When a is positive. When a is positive. n is larger than 1. The absolute value of a is larger than 1. then we can have this result. We still work based on the tables, but I need several different terms from the table, and also I need to make some change, some calculation. So final result is this one. Okay, we already have this case. And the second case I want to discuss is if we have u of n, and this is in time domain. Then in frequency domain, by Fourier transform, what it is? This will be 1 over 1 minus e to negative j omega, and plus here's a summation. K run from negative infinite to positive infinite. Can't remember. And they check the table. Fourier transform. I think it should be third one. Okay, so u of n is here. This one. So plus that is let me copy it. It is pi times dirt of omega plus 2k pi. Okay, is it this one? It is one. Then when you perform, for example, just use example. We consider the step response of y of n minus 1/2 y of n minus 1 equal to x of n. We consider this one, step response. Yeah, this main problem is how to find the particular solution, right? The homogeneous solution, that will be 1/2 to the n times the constant, right? So for a particular solution, we use the Fourier transform, right? By dt of t, discrete time Fourier transform, we have y of e to the negative j omega, or equal to 1 over 1 minus 1/2 e to the negative j omega. This is the frequency response, times, now x is we consider the step response. That means input is step, unit step, right? So this is in frequency domain is 1 minus e to negative j omega 1, and plus that summation pi deltas omega plus 2k pi. Okay, I just have enough space. K run from negative to positive infinity, right? Like this. Alright, what is this one? The first part is not hard, right? It's 1 minus 1/2 e to negative j omega times 1 minus e to negative j omega 1 over it. And what is second part? It's a summation k run from negative to positive infinite. Here's a pi, the constant. Okay, then we have a dirt of omega plus 2k pi over this 1 minus 1/2 e to negative j omega. Oh, this one looks very complex. However, if you use a graph to show these summations, you will see they are not so complex. The first one is summation pi dirt omega plus 2k pi. What it is? At every 2k pi we have parts, and the parts k times the parts. So every 2k pi, 0, 2 pi, 2 of 2 pi, 3 of 2 pi, and so on. Negative side is similar. This is omega, right? And okay, this side will be, you have parts at pi. Yeah, parts at pi. So it is just a sequence of parts. So this one is a sequence of parts, and all these parts has same peak, is a pi times of unit parts, right? Then what it is? You see this one? This one is a function. This one is a function. It could be different value for different omega, but here if omega is not 2k pi, this part is 0. This part is 0. This part, no matter what is the value, the divide by 0 divided by this number is always 0. So we can, the graph should be like this. This is a third omega plus 2k pi over 1 minus 1/2 e to the negative j omega. This one, suppose this one, I don't know what it is, I just gave things like this. Or maybe not like this, or I just illustrate something. This is this one. And the third, this one has period 2 pi. Every 2 pi, this is periodic because the e to the j omega is e to the j omega, negative j omega equal to cosine omega minus j sine omega, right? So period is 2 pi. And the delta also, every 2 pi you have parts, right? Every 2 pi you have a part. And between these two parts, the value, because it's delta is 0, so delta divided by this is still 0. No matter here's what it is, maybe like this, or maybe like this, anything, doesn't matter. So we only need a value here. Okay, so you see, this one is also a parse, sequence of parts, but here's not times pi, here's times pi, here's a pi over this, and what it is, the peak value will be pi over 1 minus 1/2 e to the negative j omega, and omega is 2k pi. Okay, when omega is 2k pi, what it is? E to negative j omega, when omega is 2k pi equal to cosine 2k pi, right? Minus j sine 2k pi. So it is 1. This is 1. So 1 minus half. So this one gives us 2 pi, right? Pi over 1/2. Pi over 1/2 is 2 pi. This part is 1/2. So it's 2 pi. Okay, so you know the parts now is 2 pi parts. 2 pi parts. Got it? And so we can have the result like this. It will be a over, I need to perform partial fraction for this part and keep these, but we know pi over these, actually it is 2 pi. So it will be this one. 1 minus 1/2 e to negative j omega plus b over 1 minus e to negative j omega, and plus this is 2 pi summation of all these parts. Right, we have this. Okay, yeah, the light is not so stable. Alright, what are these a and b? We want these two, summation will be this. So we have the constant a times 1 and the b times 1 should be that 1. A times 1 plus b times 1 equal to 1. And a times this exponential power with negative, and b times this half exponential power with negative should be 0, because this side no exponential power in the numerator, right? Okay, so this will be negative a e to negative j, just a, I just put coefficient will be fine. A times this, negative 1, and minus half times b, and the exponential power should be 0. So we have these two. Okay, so this one gave us a equal to negative b over 2. and then we put this together. We have negative b over 2 plus b equal to 1. So half b equal to 1. So b is 2. And then a is negative b over 2, right? Negative b over 2. Alright, so we have a and b. Okay, now we have y in the frequency domain. It is a is negative 1 minus 1/2 e to the negative j omega, and b is 2 over 1 minus e to negative j omega time plus 2 pi summation of those parts. Alright, you see, what is this? It's 2 of u of n in frequency domain, right? So we have by dt ft go back, the inverse, go back to time domain. It is y of n equal to, this is a negative of 1/2 to the n u of n plus 2 of u of n. So we can have the particular solution like this. Alright, yeah, this is special case when we have kind of things like a sequence of a lot of parts. Now how to work. The key problem, the key feature for the parse is like this. The parse has parse, right? Between two parse, the only value are zeros. So when the parse times with any kind of function, this part tend to be 0. So the result is also a sequence of parse. So sequence of parse times with any signal, you get another sequence of parse. Of course, the amplitude, the peak value might be varies, depending on what is that function. And here, this is just periodically. So all these parts, they have same peak value. Right? Yeah, if this is different, maybe the peaks might be different. But in our case, in this course, I think we only have this case. All of them they are same. Yeah. Okay. This is a u of n. And actually, we have some similar things. We can check the table again. Oh, this is no table. See, we have this, 1. Okay, this one, we also have parse, you see. So in time domain, it is just 1, always equal to 1. Then in frequency domain, it is a sequence of parse, peak value is 2 pi. And the u of n, we have parse, in sequence of parse, and we have more here. We have 2 here. Here's an exponential power. Then here's also a sequence of parts. Here's a cosine. Here's also a sequence of parts. These two related with the sinusoid, right? E to the j omega 0 n, that is a cosine omega 0 n and the sine omega 0 n. Combine them, right? Combine them together. So we have this. Now we can have a look. The first one, okay. Oh, it's too small. Yeah. All right, let me copy it to my book, my notes. 1 going to sequence of 2 pi dirt of omega plus 2 pi k by dt ft, and e to the j omega 0 n. Also go to summation 2 pi with dirt of omega minus omega 0 plus 2k pi, and the cosine omega 0 n plus theta plus phi. Go to summation pi e to the j theta times dirt omega minus omega 0 plus 2k pi 2 pi k, same thing, and pi e to the negative j phi, then delta of omega plus omega 0 plus 2k pi. Okay, we have these three, and what are these steps here? Okay, I give a. Actually, if you just look at the formula, it's hard to see what it is. But if you give a graph, it won't be so difficult. You see this one, k around, yeah, all the k's, k should be any k, negative to positive infinity, all the integers. So you see all the parts occur at 2k pi. So, right, 2k pi, 2 pi, 4 pi, negative 2 pi, and so on. And here's the parts is 2 pi of the parts, right? Unit parts times 2 pi. Unit parts times 2 pi. This is 1. This is 1. This is similar with the unit step. Unit step, what is, here, what is 1? 1 is, yeah, I give a graph here. This is 1. This is 1. Always 1, right? And by dtft in frequency domain, it looks like this. It's a parse, right? The parse. It will be 2 pi times that, and for every 2 pi. Okay. So this is 1 to here, and we just have the unit step, right? This is unit step. This is 1. This is a u of n, and this one is dtft. We already have this is pi dirt, 2 pi, 4 pi, 6 pi, and plus 1 over e to the negative j omega. No, this one is this one. This is like a half of it, right? Half of it. You remove this part, you only have half of it. So this is half of this, you see? Half of this. But we also have this one. We also need this one. This is u of n. And then we go back to here. E to the j omega 0 n. E to the j omega n is what? This is a kind of a cosine. The real part is a cosine, and the imaginary part is a sine, right? It's a combine of how to give the graph like this, right? Y into this, y into this, y into this, right? It's a cosine. This is a sine, and the sine is in the j. With a j in front of it, the combine of these two, right? Combine of these two, yeah. And by dtft, is this one is 2 pi times parse, and the parse happen parse at 2k. Is omega 0 minus 2k pi, right? Omega 0 minus 2k pi. So it is omega 0, like omega 0, then omega 0 plus 2 pi, omega 0 plus 4 pi, and omega 0 minus 2 pi, and the parse. Parse the parse 2 pi. Parse is 2 pi. Here's 2 pi. 2 pi of the unit parse. So shifted by omega 0. Seems like this one. 1 in frequency domain shifted by omega 0. Then in time domain is this one twisted. You see? This one twisted. Now you can imagine this is something like this, but twisted, and twisted and go into the complex numbers. This is a real number, right? Just 1. You twist it and separate it as 2 parts, go into the complex number space, and you have things like this. All right, yeah. So this is the e to the j omega n, and omega 0 is the frequency of it. So this one has a frequency omega 0, right? Omega 0. If you just look at the period from 0 to 2 pi, you look at this part, you only have 1 part. So we have discussed before, right? For discrete time signal, you can think the frequency just 1 cycle from 0 to 2 pi. You can think only frequencies from 0 to 2 pi. All the rest, they can move equal to something inside 0 to 2 pi. And here the parse is here. Here the parse is here. Alright. Yeah. Alright. Then cosine. This cosine one. Cosine one. Cosine one we have 2. Now is what? Each one is a parse, but at different place. This one is a parse at 2. It's omega 0 minus 2k pi. This one parse at this one for these, and this one is negative omega 0 minus 2k pi. So you can think every 2k pi plus omega 0 or minus omega 0, you have 2 parts. So omega every 2k pi 0 2 pi, then 4 pi, right? Then you have, here's omega 0, here's omega 0. Then you have 2 parts here, 2 parts here, 2 parts here. So every 2 pi, nearby 2 pi left and the right, you have 2 parts. The distance is omega 0. You have 2 parts. And the value here, what is the value here? How many parts? Is pi times this phi j theta. Theta is the phase angle. So this value depending on the phase angle. Actually, this one is a complex number. This is a complex number. So the graph here, I just the illustration. This will be a complex number. So here's complex number, 2-dimensional. And this value will be a complex number. It's pi times this, or pi times negative this. So these two are different. Actually, these two are different. This is a pi. Here's a plus omega 0, right? Plus omega 0. Here's a pi e to the j theta. And this is minus omega 0 according to pi e to the negative j theta. The thing like that. And if you just look at 1 cycle, for this time maybe look at from negative pi to 2 pi, negative to positive pi will be better. You look at this. This is a main interval for the frequency. You will see you have 2 parts, omega 0 and negative omega 0. You have 2 parts. These 2 parts according to this one. So time domain is a cosine and the frequency domain is 2 parts like this. Alright. Oh, it's a time. Okay. That's all for today. Alright. Then see you next time.